thanks for coming, everyone. Thanks for staying till the end of the conference. And hopefully, we'll be talking about something interesting today. Right? We've heard from Tse about the compute and the modeling layer. I don't know if you went to Tyler's talk earlier about how AI is also becoming like compound AI systems and AI applications. Well, this talk is about sort of the foundation for that, which is the data. And new challenges that AI data brings, and the new types of databases, data lakes, and how we deal with all of that data. So as Tristan mentioned, I'm the CEO and co-founder of LanceDB. We create a new columnar format called Lance that is optimized for multimodal AI data. So think of it as Parquet, but for AI data. Around this, we're building a database for AI called LanceDB. It includes vector search, but a lot more. So colloquially, I've heard people describe LanceDB open source as SQLite for vector search, or SQLite for sort of dealing with AI data. Once upon a time, I was also, I think, contributor number 2 to the Pandas library. So I spent a lot of time building tools for data scientists and machine learning engineers. Spent a lot of time doing recommender systems at TubiTV just before founding LanceDB. If you want to chat with me, I go by the same handle on Twitter and GitHub. So it's Thursday afternoon, and it's a little low energy. So let's start with a bang. So my prediction for AI is in 3 years, vector databases won't exist. And now you might ask, Chang, isn't LanceDB a vector database? Why are you saying this? And the reason why I'm saying this is not that vector search won't be needed in 3 years, but that it will appear in a very different form. Vector search, I think, will become a feature rather than a product. And the core problem that it solves today, which is retrieval, will come in a new form that includes vector search, but also so much more. As evidence, I put up a landscape chart of all the different vector databases that are available today. So you have pure vector databases like Pinecone and Quadrant and Vespa and all of that. You have traditional databases, NoSQL, SQL search engines that are adding vector indices. And typically the difference between these are things like databases that are adding vector indices have some difficulty scaling up to large-scale vector datasets. And whereas things like pure play vector databases are lacking in features around like data management. Most of these pure vector databases, let's say, like can't even handle more than one vector column per table or per collection. So it makes it difficult to do experimentation. If you want to try like 3 different embedding models or something like that, you have to like have 3 tables or 3 copies of your data. So I don't know if you've heard. I think my friend Billy was retorting the other day is like, oh, these are just dot product as a service, which is kind of silly. Now, with so many choices, you might ask, okay, well, like, should we just basically just wait or like pick the one that I'm already on, or just wait until one takes over and AI infrastructure is solved? Now, we're going to spend the next, 30 minutes together, so it's going to be a really boring talk if the answer is yes. Right, so one is, at the top in the production scale, if you're enterprises with millions to multiple billions of vectors, like especially in one single data set, that is still not a solved problem. Existing systems, existing databases that have added vector indices typically can't handle this type of scale. Pure vector databases, maybe a few of them can handle the scale, but do it in a way that is really complicated and also super expensive. More advanced retrieval is also not yet a solved problem, right? So last year everyone was building sort of demoware in hackathons, vector search worked great. It looked great, it was simple to build. But as people put AI applications into production, you find that, hey, simple vector search isn't enough. How do I get from 65 or 70% to the 90% retrieval results that I need for a production AI application? So what we need is multiple recallers, multiple ways to retrieve data other than vectors. Even within vector search, embedding generation is also a huge pain. And then when we have different ways of retrieving data from full text index, maybe SQL and vectors, how do I actually combine and re-rank them? And then in terms of retrieval, sort of self-improving retrieval doesn't exist yet, right? So if you think about sort of this advanced retrieval process, at the end of the day, that embedding model is static and is not really tailored for your data set and for your use case. But as soon as you build an application, you have users, you get feedback, you can actually start to feed that data back into the model and fine-tune both your re-ranking process and your embedding generation process so you can get much better retrieval results as time goes on. So, and sort of most importantly, right, there's more than just embeddings to think about. You have text documents, you have images, you might have videos, PDFs. It's really difficult for vector databases and even just any traditional database to manage all that data. And so the consequence of that is we have a lot of problems dealing with everything else outside of just pure simple vector search. So we can zoom out a little bit and talk about what do we need to build the data foundations for AI outside of retrieval. So the activities typically I see break down into a couple of very rough buckets. So one on data exploration and data preparation, one on training, maybe fine tuning, one on just analytics and evaluation, and then sort of what we think of as vector search and vector databases today fit into this fourth bucket of serving and real-time serving. So for data exploration, think about it as I run some SQL query that filters the metadata, and then I need to select the right pieces of the raw data and then visualize it and show it to the user. For training, right, it's the same metadata for sampling and shuffling, and then I need to load the tensors, maybe stream it from object storage into my GPU. For evals, I'm running OLAP queries, maybe on log data or on the semi-structured data that's coming out of the model. And then for serving, it's about metadata for the filtering, vector search, and then also possibly raw data to serve back to the user. Now, vector databases, as you see them today, is sort of this thing that's a little bit off to the side. You have to create another copy of your data or parts of your data set and load it into this thing. And it's really slow to load. It is only good for that one type of query. And then you have to manage additional data sources and systems for all of the other things that you do throughout your AI workflow. Right. So basically the take that I have earlier boils down to this, that vector search should be natively accessible anywhere within this workflow, not as a separate thing that you have to manage, not as a separate thing that you have to pay for, but as part of a sort of unified data foundation that is available for you all across all of 4 buckets. Right. So why doesn't that exist today? What is the problem? The problem is because AI data and AI workloads are very different from traditional tabular data, and today's data systems and data formats are almost always optimized for tabular data. So this is what I call the sort of CAP theorem for AI data. Is AI data typically means not just the tabular data, that's the metadata, but also large blobs. Think images, think vectors are also much larger at the record level. you would need fast scans, for these overlap queries and filters, and you also need fast random access. So for data exploration and for quick fetching and serving. So for example, like how many of you know what Parquet is? Okay, great. And then how many of you know what a row group is in Parquet? Okay, still good, half of you. So basically the idea, so we all know about Parquet, it's super popular, it's great for tabular data. The issue is if you want one row out of your Parquet data set, you have to read out the whole group. Typically that's, that can be like 1,000 to like, I don't know, 10,000 rows or something like that. If we're dealing with tabular data and you have to read out 10,000 floating point numbers, not ideal, but it's not that big of a deal. But if you're storing images or if you're storing like Eta2 vectors, that can become prohibitively expensive, right? And so formats and systems today essentially is only good for at most 2, but most of the time only 1 of these requirements. And so the consequence of that is we can't have a single system that's good for all of the different activities you need for AI data. That means you have to have multiple copies of your data in different places, serving each bucket of workloads. And so it's very expensive, and it's also really complicated and error prone when you spend all that time and effort in converting data to and fro. The operation of those multiple systems is also really complicated. So Lance users also come to us, and typically they'll tell us that like, hey, we manage a lot of like visual data sets, and the conventional wisdom is the exploration part and the training part is 2 separate systems. So we had staffed up separate teams and like budgeted for 2 separate systems and 2 separate copies of your data until we discovered Lance, and we found, okay, you can actually have just one thing for that. And that saves you a lot of complexity. And then the last thing is most of those data formats and systems sort of don't really bridge that gap between object storage and your GPU. So you have to spend a lot of time in that like training IO phase, and it really hampers your GPU utilization, especially in large distributed training scenarios. And this is another core problem that LanceDB is designed to solve, or Lance is designed to solve. Right, so the solution, of course, you can probably guess the answer, is Lance formats, right? So Lance format is a columnar format. It is optimized for AI data. It's a single source of truth, both for your offline and online use cases. There's no wasted copies to support schema evolution. So when so a bunch of our users that are managing large visual data sets, one of the big benefits they tell us is, look, when I want to run an experiment, before I use Lance, I have to like copy my like 10 terabytes of images down to local disk, like unzip it, and like, okay, add in some feature data, zip it back up, and like throw it back into S3. This is not only costly, but also take like a day or something like that just for one experiment. And because Lance is a columnar, it also presents an Arrow API. It also means your data is now much more structured and organized. So rather than writing custom scripts to manage 3 different pieces of data, like your metadata, raw data, and all that, you can write SQL, or you can write data frame APIs. So it's much easier for that data pipeline for unstructured data. And then lastly is when you have data exploration and training, share that same data, but not only that, you can actually, the serving system can also share the same data as well. Right, so how do we achieve that? So just, I won't go into too much detail, I promise, but with Lance format, the layout is different from Parquet, so that we provide sort of sublinear lookups for random access, and it's columnar, so it still supports very fast scans. The IO execution subsystem is optimized for large blobs, and we do that through lay materialization. And so the trade-off here, right, you might ask, is that there's no free lunch, right? So in order to support fast scans and also fast random access, it means you can't do sort of file level compression in the same way that Parquet does with, let's say Snappy, or you can't use like gzip on the data. So instead, we build in advanced encodings. So right now, Lance supports dictionary encodings, and then over the rest of the year, we'll be adding a lot more advanced encodings for the tabular data parts, for like time series data, for floating point string data, and so on and so forth. And one of the great things about Lance design is that the encoding subsystem is designed as a container, so you can plug in advanced encodings for various different data types, and this is more relevant for AI. So if you have, let's say, point clouds, for example, you can take like lossy floating point compression and encoding algorithms and plug that into Lance and be able to deal with that point cloud data and much easier than like trying to add in a new type of encoding into existing columnar formats. One of the things that's really interesting about Lance is it's more than, so there's the file format, which is like the equivalent to Parquet, and then there's a table format that supports schema evolution, versioning, reproducibility, and then there's an indexing subsystem. So you have like a vector index, you can have a full text index, and then you can have we call scalar indices that are like traditional like B trees and bitmaps on columns that you want to filter on, right? And so all three things, when each one is fairly interesting, but it's when you put the three of them together that a lot of the really magical seeming benefits for AI data comes to the fore. So for example, people are like, okay, it seems magical, we can unify training and exploration. Well, that's only possible because we can do fast scans and we can deal with random access. When we say, okay, we're much more generalized than just a simple vector index, it's because you can build indexing subsystems for Parquet, but if you have to read out the whole row group to get to the rows that your index is pointing to, it's, you don't get the same performance benefits of an index. It's only when you support fast random access that actually makes sense. All right, so Lance format becomes this I call it open platform to build on. So you can have SQL, you can have data frame workloads for analytical queries. We ship a PyTorch and TensorFlow data loaders for training. And then, of course, we have LanceDB, which is for vector search and retrieval in general. Okay, so how do we go from a data format to what I call a composable lakehouse for AI? So this is sort of drawing the rest of the owl, right? So let's break this down. Like, what does the lakehouse look like? Well, so I've got a storage layer, or maybe some indexing, and then in offline use cases, typically like training and querying, and then online sort of like serving for vector search and things like that. And of course, data exploration is typically like a sort of user interface layer that's built on top of this querying and maybe training capabilities. So at the exploration layer, we need to do search to find maybe like duplicate images, to find similar images, filters, and then we need to be able to visualize the results of those. For training, of course, connecting to PyTorch and TensorFlow. For querying, both sort of SQL engines, distributed query engines, and then like data frame libraries. And then for online, like vector search and retrieval and search engines. All right, so underlying all of that is basically Lance format plus the Lance indexing layer, and so you can have the same sort of data layer for across all of those things. And one of the really interesting things about this is being able to unify offline and online data makes it really easy to bulk load data into your online serving system. So I know previously I was at TubiTV, the streaming company, and we had sort of offline system that was like Spark and Parquet, and then online feature store that was was ScyllaDB, and so you could only load data in like small batches across the API. So then what happens is at scale you have these like daily feature loading jobs that run for like 48 hours, right? And whereas, if your data is in Lance, you can basically just have your Spark cluster write your data to Lance format, and then you can point your serving system to that location, and then that's it. So we'll have a blog post on this soon, I think. That's probably going to be titled something like, ingesting and embedding the internet in like 10 minutes. Okay, so let's break this down. So let's talk about what the online world looks like, and then what the offline world's going to look like. So what we're building in this online world is LanceDB, and what we're building is essentially self-optimizing RAG. So not just simple vector search, but production quality retrieval, and not just production quality retrieval, but it's a retrieval system that gets better and better the more you use it automatically. All right, so first is we have LanceDB. It's lightweight, it's open source. There's no sort of servers to worry about. People have compared us to SQLite for vector search. Turns out because of Lance format, it's also really scalable. So for LanceDB enterprise customers, we deliver a really scalable, performant, but also incredibly cost-effective vector search engine for them. And not only is it great for vector search, but LanceDB contains all the rich features that you need from hybrid search that includes full text index and SQL filtering and also re-ranking. So the screenshot you see on the right hand of the slide is one of LanceDB community users that built a semantic search tool for Twitter for his own tweets. But one of the primary reasons he chose LanceDB was, hey, I can do time-based filtering. I can like search on the links or the media that comes with my tweets, and I can sort of limit by number of likes or retweets and all sorts of things that I like to do. Right. Another thing that's really interesting for LanceDB users is the ability to plug directly into object storage. So we can run with your data directly from S3 or GCS bucket or any of the sort of S3 compatible APIs. So for example, you can, with LanceDB open source, you can put your data in, let's say like S3 Express, and you can run LanceDB inside an AWS Lambda function, and you can get serverless vector search, that returns in like maybe 50 milliseconds or so, and it scales down to zero cost when you're not really using it. Well, not zero cost for the compute, right? You pay a little bit for the storage, but that's nearly zero. And a lot of LanceDB users have been reporting that actually as they find different ways to improve their retrieval quality, fine-tuning not the LLM, but the embedding model is actually really effective. So this screenshot is from Chris Moody, who's one of our users, who fine-tuned his embedding model and found that even with maybe about like $10 worth of synthetic data, he can get much better retrieval results by fine-tuning than at the time what was the top of the MTB leaderboard. Right? So with fine-tuning then becomes a question of like, where does that feedback data come from? How do you manage that feedback data? And how do you sort of interact with the model to go through the process of fine-tuning? And so we're using, and because LanceDB is based on Lance format, that's really easy for them to do. It's like you have data that comes in as an error table, you write it to Lance format, and it connects easily to like Pandas or Polars or PyTorch and Hugging Face. Like you can write Hugging Face datasets directly into Lance as well. All right, so when you put all that together, right, the sort of final say and form of this RAG system is basically just a recommender system in disguise, right? So you have multiple recallers, right? Semantic search, full text search, and then you have a re-ranking system, whether it's through let's say Cohere's re-ranking API or your own Hugging Face re-ranking model, or just a simple linear combination. You get better results than each recaller alone. And then as you get responses, you can use that to fine-tune both your embedding model and your re-ranking model. So if we zoom further out from the perspective of a user, it means I'm giving this system raw text or images. I don't really need to worry about embedding generation or like configuring all the search. I can just start interacting with it in natural language or even giving it images to retrieve context. And then the more I use it, the more accurate it gets over time on my data set. All right, so that's the sort of online system that we're building as LanceDB. What does the offline side of things, the offline part of the Lakehouse look like? So what Lance provides is we call a one-stop shop for managing all of your multimodal data. So you can do explore, train, and then rapid experimentation. And what's really interesting is, I think what I call declarative AI. So most of this is open source right now. So we'll take a look at like what people are building on top of Lance format and LanceDB open source, and then I'll give you a little preview of what we're building out as well. So let's take a contrived but probably plausible pipeline for like processing your images, right? So you have raw images coming in. The print might be a little bit small for the back. So you have raw images coming in, and then you say, I'm going to crop the image to the standard dimension, and then I'm going to sample it, and then I'm going to take that clean image, and I'm going to generate 2 different embeddings using clip and visual BERT, and then I'm going to extract a bunch of features using, let's say, like some pre-trained YOLO V8 model to extract, like all of the number of people and their locations from this picture, right? So today you write some script that like requires like PyTorch and a bunch of like data manipulations, maybe some like throw in some OpenCV in there, and then when you have to, this is like one pipeline out of maybe like hundreds in an enterprise, and then you have to like manage it in production, and it's very easy for something to go wrong, and you spend all of your time sort of dealing with that. So now instead of writing that Python script, what if all it required was a table schema declaration, so that you could say, okay, this table has an ID column and a raw image column, and then the clean image column is just a sample of the crop of the raw image, and that is just if you're familiar with like virtual columns or derived columns, and then the 2 different vector columns are just using the vector field applied to the clean image for the clip model and the visual BERT model, and then the people is a list that is the output of some YOLO V8 model, right? So from the perspective of user, this is much easier to think about, and as a system, we can then hide all of the computations and the operational complexities behind this. So we can separate what people want from how to do it, and that makes the whole system a lot easier. And another really interesting area about what I call declarative AI is in interactive data exploration. So how many of you guys know what YOLO V8 is? Okay, so YOLO V8 is probably the most popular computer vision model, and so the current implementation is maintained by a company called Ultralytics. They've released a project called Ultralytics Explore, which allows you to load an image data set with metadata, like run SQL filters on it to filter that data down. It allows you to ask, they have an Ask AI feature that's like, show me images with 10 people or something like that. And then you can see sort of the preview your images that's a result of these filters. So from the storage to all of the queries, LanceDB is the sort of the query engine that powers all of that under the hood. And so this allows a lot of ML engineers to then say just write SQL against a bunch of images and be able to preview their data and curate their data and be able to label their data a lot easier than before. Right. Okay, so from exploration, now let's talk about large-scale data processing. So Lance is connected to, to SQL engines and data frame engines, and also distributed engines through the Apache Arrow interface. So whether you're used to DuckDB, Pandas, or Polars, you can query your Lance data directly. And then we're working on a JVM bridge so that it'll be much easier to say like query your Lance data in using Presto or Trino, and then we can make bulk ingestion a lot easier as well. Okay, so that was sort of the so exploration and compute part. So what about training? And so you can see in the screenshot, so Tanay is a Lance community member. He's also a Kaggle Grandmaster. So he's put together these training workflows and tutorials on, okay, how to use the PyTorch data loader for Lance with a sampling tool to make it really easy to do pre-training on your LLMs. And in his words, the big benefits that he found using Lance was it's really easy because everything's just in one place. And he saw something like 95% average GPU utilization, which typically is much higher than what he's used to with other tools. And then he felt like it was a lot simpler for him to build it this way because you don't need to spend time and effort, converting between the metadata for filtering and sampling, and also like tensors that are either like tensors or blobs for the training data. And then the last thing that's really interesting that the community have given us feedback on is the versioning and schema evolution features in Lance really helps people move faster on ML experimentation. Right, so I mentioned earlier about the user that's like, hey, every time I run a new experiment, I have to load, round trip, all of my data, and then just to add one column. And it's expensive and time consuming. Because of the Lance table format, you can just say, hey, I'm going to add a new column. You just write one new file, and then there's a new manifest version that then marries the old version, old schema, and the new schema. And so if you're connecting that to a SQL engine or data frame tool, you'll automatically pick up this new column. Right? And then beyond that, support, all the versioning is automated, so you don't have to manually mess with anything. Every time you do this bulk operation of adding rows or updating rows or adding and removing columns, this is automatically tracked for you. And so that means you can also travel back in time. So if you, let's say you loaded a bunch of data into your serving system and you're like, okay, I screwed up somewhere and my Datadog is screaming at me. Within 2 seconds I can say, go back, use the version of the data before I loaded all of this in. And so that's pretty much an instantaneous operation because it doesn't require a data copy. It's just changing the manifest file that is pointed to. Right? Cool. So I've thrown a lot at you, but there's a lot more exciting stuff that's to come in Lance. So for the next quarter, we're going to be working on sort of three big topics. One is optimizations for vector indexing, so fully supporting BF16 and F16, or possibly even smaller sort of quantizations. Additional indexing types, and then maybe clustering order for vectors to boost the random access performance even more. We're working on sort of what we're dubbing V2 of the format. So there's some gaps in null support that we're going to be addressing, and then adding in a lot more advanced encodings, for more tabular data. So that once that's in place, Lance will not just be great for AI data, but it'll be amazing for just traditional tabular and OLAP use cases as well. And then lastly is integration into the rest of the ecosystem. So Lance's main API is Apache Arrow, which makes it really easy for us to plug it in to many different systems today. So if those systems have like a Rust or Python API that's already workable, the sort of fly in the ointment typically is the JVM ecosystem. So we're building that JVM bridge today so that we can have a native like Spark data source, and also things like Trino and Presto integration. And then through Arrow, we're also going to be working with AnyScale folks on integration with Ray. All right, so that's sort of the end of my talk. I think if you forget most of it, it's a lot of like low-level information. I think the thing that you should remember is like narrow vector search should become a feature. And I think as like people working on AI or machine learning, what we deserve is not have to spend all of our times copying data from and to as we move from one activity to another, right? We should have a single source of truth, a stable foundation, both for storing and managing that and querying that data, and that we can have one single system that does way more than just simple vector search. So we're open source, both the data format and the embedded vector database. You can find us on GitHub. The QR code is for our Discord community, so if you want to come drop in and ask questions or just see what people are building, you're more than welcome. If you want to talk shop, I'm Chang at LanceDB.com. All right, so thank you very much.